So let's just continue our little dive by looking at the Hertzian dipole in particular, just to give you a little flavor as to where these equations come from. So a Hertzian dipole is a basic kind of antenna, and it's probably the simplest kind, where your antenna would just radiate with a positive and a negative charge, where your current represents itself as a really short segment that's close to the origin, going up and down in the z direction. So let's take a closer look at what the electric and magnetic fields are, and where you would develop this directivity equation. So when you're modeling this Hertzian dipole and trying to figure out how it works, you start with the fact that your current density, so this is the current that you're feeding into the antenna to create the radiating electromagnetic wave. It would be some current, like I said before, across an infinitesimally short length along the z direction, and infinitely small in the x and y direction, so we'll use delta functions to describe them. And in this case, if we define the dipole as positive in the positive z and negative in the slightly negative z direction, the current will be defined as, in this case, let's say the current is in the z hat direction. Now, using this, you can come up with an equation that represents the electric field in polar coordinates. So the electromagnetic field components are as follows. There is an electric field component in the r direction. So r theta phi is going to be equal to 2 eta I delta z e to the minus j beta r all over 4 pi r. And then you're going to have a few terms here. 1 over jk r squared, so something that's a function of 1 over r squared, plus 1 over r. And then cosine theta. Next up, there's the E field will also have a theta component. And that is going to end up being this. Now I'm just going to order this by the power of r. So you have 1 over jk r squared plus 1 over r plus jk in sine theta. And then finally you have a magnetic field component that's going to be in the phi direction, so always perpendicular to these electric fields here. And that is going to be e to the minus j beta r over 4 pi r. There's no 1 over r squared term, but there is a 1 over r minus jk sine theta. So the main reason I wanted to bring this up is to point out that when you factor everything out, you have 3 terms, right? You have a term that's independent of r, and then you have terms that's proportional to either 1 over r or 1 over r squared. So these 1 over r squared terms, these are called the near field components. So note that while you're close to the antenna, these are non-trivial, right? But as you get farther and farther away, as r increases, these will go away. So this antenna has a set of near field components. They go away as r increases, and usually what ends up happening is that the near field components end up being responsible for the reactive components of the impedance of the antenna. So what you'll find is that if you treat your antenna as a load because you're driving it with some kind of voltage at the end of some kind of transmission line, in many cases there's going to be a reactive component that stores energy and releases energy, and all that is just all stored in the volume region that's close to the antenna. Now as R increases, these terms go away and you're left with the far field components. And the two things to observe is that they become dominant in the far field, so which we define as Kr greater than 1. So once you get a certain distance away, especially if you're on the receiving end of the antenna, then usually this is the only term that you have to worry about. And in this case, if you look at what components have far field components, you can see that all the radiation occurs in E theta. The magnetic fields will all radiate in the theta direction, and the H field will be in the phi direction. So as you're far away from the antenna, these are the only two components that you see. So as this propagates far away, we'll see that the field that we'll actually see once we've left the immediate vicinity of the antenna will be a theta direction, which is jk eta I delta z e to the minus j beta r over 4 pi r sine theta, and then an h phi component that is equal to jk I delta z, so you take out the eta, and then e to the minus j beta r over 4 pi r sine theta. And if you look at this, these are, if you just choose a particular theta, these are all real numbers except for the e to the j beta r. So you see that this is actually a set of equations for a plane wave. And so with that, you can get the Poynting vector and the time average power density, which is 1/2 the real part of E cross H conjugate. And you'll also see that the field pattern varies as a function of sine theta. So f of theta is going to be equal to sine theta. Now, one of the things is that you will also be able to show that the maximum value, if you put this f of theta equation into this d of theta phi, you can find that the maximum value possible is going to be equal to 1.5. And so your expression for the directivity for Hertzian dipole is going to be equal to 1.5 sine theta squared, which is what we're showing here. And also seems like I've forgotten this squared here. So to quickly summarize, we introduced the concept of directivity, which basically tells you how much of the power density in a given direction there is as a normalized by the average radiated power density. So in the case of isotropic, if it's just 1 everywhere, and if you're just looking at it in terms of theta, it would just be this nice circle here. So the antenna is equally sensitive in all directions, or radiates equally in all directions. Another example we saw was the Hertzian dipole, where you just have a lobe that's maximized along the z equals 0 xy plane area. So if your dipole is right here and you're dead on to it, then you get the maximum amount of transmission or maximum amount of sensitivity, and you get the weakest amount of transmission or sensitivity if it's coming down from the top. We also took just a little bit of there's also a simplification equation here, where if you know what the maximum directivity is, you can also just write this directivity as the maximum value times times the field pattern squared. So then you don't have to do this whole integral. You can just take the maximum value and square the field pattern. And then we also took a little look at the Hertzian dipole in particular, how you come up with the directivity. So the general formula is you start with a current density, you evaluate the field, and we also came across the concept of a near field and a far field component. So as you get far away from the antenna, the far field components are the only parts that matter. But in the near field, you have this region where you can store and extract energy. And so quite often, if you treat your antenna as a load and you're feeding power into it, if there's a reactive component, it's usually due to these near fields here. But if you just look at the far field component, you can extract the fact that the field pattern looks like sine theta, and from that, if you stick f of theta in, you can calculate what the maximum is and use that to come up with the directivity of the Hertzian dipole over here. And so with these tools, if you were given an antenna pattern with a current density, you can kind of see the process that you go through to figure out that in turn how that gives you the directivity, which tells you how good the antenna is at transmitting and receiving as a function of direction.